All right. So yeah, thanks again, Tim. Uh, so Tim has already gone through a bit of the hardware and the QFLEX technology that we're bringing in this device, but uh, basically, so what I'm going to do, I'm going to go over a little bit more on the hardware side, and then I'll tell you the different software options we have, and following the demos, of course, right? So I will demo both two software options. A number of you, actually, like 80% of you, are using an embedded platform. So you'll be happy to know that that will be part of the demonstration as well. So I'll make sure we highlight that, and hopefully you'll have some questions for us regarding that front. So in terms of system hardware, I think 30% of you already have a QUBE Servo 1. So the QUBE Servo 2 has everything the QUBE Servo 1 has, right? So you have that nice compact integrated technology, right? So it's kind of a one-stop shop for like modeling, controls, and mechatronics, where you have everything embedded and doesn't take much lab space and so forth. You have two, just like the first version, we have two add-ons, right? So we have an inverted pendulum, which is mounted on this servo here, and the DC motor, so an inertial disc. And as you can see, they're easy to add, right? So if I want to put the pendulum, it's all magnetic. So these are very easy add-ons. You can just, no screws are needed. So so you can quickly change between the two experiments. There's two encoders on the system. There's one to measure the DC motor, and there's one as well to measure the pendulum angle. The DC motor on the system is direct drive, so there's no gearbox. Some additions that we've added to this is the QFLEX 2 technology, which is the first thing I want to kind of discuss a bit. So the QFLEX 2 interface is something that we're starting to use in all of our newer products. So we're using it with the Quanser Aero system, for instance, and the QUBE Servo 2. So we have two interface panels available right now. One is the USB. So this has an embedded data acquisition card, and just makes it very easy to just connect. You just connect your laptop or PC directly to the Cube with this. So that's the first option that we have, the first QFLEX 2 USB interface panel. The second one we have is if you have a microprocessor board, for example, I got the Arduino Uno here, then you can use the embedded interface panel. So that's the second interface board that we have for the QFLEX 2. So I got to connect it there. Now, if you wanted to have both, because I know some people are both, MATLAB Simulink or LabVIEW users and embedded, then you could have the two panels and just interchange them within the same QUBE servo. So you don't need a separate servo. It's all you could just swap out the actual panel, right? But that would be yeah. So you could definitely do that. The LED, like Tim mentioned, so you have a user-programmable LED, so you can use that to say when it's powered, and if there's like you reach voltage limits. Other things we have, so besides the two encoders, we also have a current sensor on the QUBE Servo 2, which we didn't have before. So we have a current sensor that allows you to do certain experiments, like parameter estimation if you wanted to, and a speed sensor. So it's a digital tachometer that is within the system, right? So it's actually it's something that's part of the driver and allows you to get velocity measurements without having to use the encoder. So that allows you to do like very optimal speed control, for instance. So there's little add-ons, voltage protection and thermal shutdown of the amplifier, and also stall detection and warning. So the amplifier, if someone would stall the motor after a few seconds, the amplifier would stop, would automatically shut down, and it would prompt the user a flag saying that a stall error has been issued, and then you could just re-enable the system and run it again. So those are some of the additions that we have for the QUBE Servo 2, and again, it has everything QUBE Servo 1 has, and we just added a couple more sensors and some more protection and the QFLEX 2 technology. So software options, we've already talked about we have so for the USB panel, you can use MATLAB Simulink using the Quanser QUARC graphic controls prototyping software. We'll also be having LabVIEW, so they'll have using our QRCP add-on, you'll be able to use LabVIEW VIs with the QUBE Servo2. That is to be released, so we will be working on that soon. And if you're using a microprocessor board with the embedded interface, then we have that option. So there's basically going to be 3 software options right now. And yeah, I think that's about it in terms of the general overview. So let's just dive in here. So I'm going to start with a USB panel. And in this webinar, we're just going to be using MATLAB Simulink, and then I'll branch off to using the Arduino. So to connect the system, I'm going to keep the DC motor. You just connect the USB cable here, and I got that already connected to my system. And now I will power the device. So I'm just going to plug this in, and there you go. It's over a bit. All right, so as you can see, the LED lit up, so it's saying that the device is powered. I'm gonna load up MATLAB here. Now, some of you may or may not be familiar with QUARC, but let me know if you have any questions regarding that, of course. All right, so I'm just going to go through a few of the experiments using a DC motor. So the first one I'm going to go through, very, very simple, and it's usually the first lab that we encourage students to do, is called the hardware integration lab. This is a nice intro to show students, okay, how do you interface, how do you talk to the DC motor, how do you talk to the sensors, how do you acquire a signal, right? So this is a very simple Simulink diagram that uses like the 3 primary QUARC blocks, right? And with the Quanser QUARC software, you can access all the sensors and actuators of basically any system, including the QUBE Servo2, using 3 blocks only, right? So the first one is a hill initialize. Hill initialize initializes your acquisition device or your actual, your DAC board or your hardware device. For example, the QUBE Servo2 has its own DAC embedded in the USB interface, right? So what I selected here in the hill initialize is QUBE Servo2 USB. So that's selected in hill initialize. Then to access all the I/O, I got 2 blocks. I got the hill write and I got the hill read. In the hill write, I'm just going to set this to 0. There's an enable, so you can disable or enable the app on the digital output signal, digital 0, and AO is analog output 0 or D to A. So you can apply a signal to your amplifier, which drives the motor. And then the LED. So the LED is right here. So when it powers on, it'll go green. And the hill read. So hill read time base I'm using right here, the hill read time base block. So I got the current sensor wired here. I got the encoder. So I'm just hooking up the encoder for the DC motor. But you could read both, of course, the DC motor and the pendulum at the same time. Then I got the digital signals that read, if the amplifier has reached any saturation points regarding the thermal aspect, thermal shutdown or whatever like that. Stall warnings, stall error flags, and also what I put in here is if it does get stalled, then it will stop the Simulink diagram. So you can use those different flags within the QUARC diagram. And lastly, I'm outputting the tachometer. So the digital tach that's in the system, I'm measuring the speed here. So using the Simulink model, what QUARC allows you to do is generate code, real-time code from a Simulink diagram. So you go to QUARC, you go build, and this generates the code and generates an executable, QUARC executable that you could run actually standalone if you wanted to. Okay, so we'll let that generate. It says it's been downloaded. Great. So then I go back. I say QUARC start. So as you can see, when the control starts running, the LED changes color, it goes green. And then I can go ahead and say, okay, let's apply a 2-volt signal. And I get my measurement. So first of all, you can see the neutral disk is moving. And then if I probe that, then you'll see the response changing the scope. So again, if I stalled it and like left it running for a bit, it would stop automatically. Okay, I'll stop that. And so yeah, that's your basic demo, kind of showing you how to talk to the QUBE Servo2. So again, you're just using three Simulink blocks that are from the QUARC targets library. So if I'm just going to show you what else QUARC does for you. QUARC targets is what gets installed. You get the QUARC menu, and using all these, you can generate code, and you can use all these blocks to talk to your I/O. Okay, great. So that's it for that one. So that's hardware integration. Now let's get into something a bit more application oriented. So we'll do one modeling. I know it's not many of you have said they do modeling, but modeling and controls are so tied together. What I'll do is give you two little demos. I'll give you how to do a short model, an example model that you could use using step response, and then we'll dive into position controller. So let's go to bump test. So bump test is basically a step response. I'm going to open this up. So here is the bump test, right? So I got the voltage and the speed here. So the top scope will give me voltage, and this will give me, the voltage is in the bottom here and the speed here. So this is your typical experimental type modeling, right? We have some other controllers as well, right? And you can create your own. Everything is fully open. Plus, all the labs we supply, as I'll show you later, this is all part of the courseware. So you have student and instructor workbooks that show you how to run everything I'm doing right now. And they have like student exercises. And then an instructor version, it has all the solutions for those. So this one has the same three blocks, right? I got he'll write analog, he'll read. Right now I'm just reading the velocity measurement. I'm using a little high pass filter. That's about it. So I go QUARC build. And this model only runs for 2.5 seconds because that's all I need to get the response. So I would go like this. So I apply a 2-volt signal, I get a step response. And if I maximize this, you'll see that it's basically a first order transfer function. So I can just use a first order transfer function to model the system, right? And just one example, another thing you could do is in order to take measurements, right? So if you want to measure the steady state gain and the time constant, in order to find those parameters, right, for your model, you can plot this in a MATLAB figure, right? So you can save data and plot it, right? So what I'm going to do here is the data is saved inside the MATLAB workspace through the scope. I run a script that basically loads the data for me, and then voila, I got this in a MATLAB figure. And then I can use my data cursors and take measurements, right? So for instance, I want the DC gain, right? So if I want the steady state gain or DC gain, I use my data cursor. All right, it's about 52.3. So 52.3 divided by 2 volts. There. So my DC gain is about 26.2. And then I can find what the time constant is, right, based on the decay and so forth. So a lot of people ask, can you run a simulation? Can you run a model simulation in parallel with the hardware? You can definitely do that, and you can do it for model validation, right? So after the student or instructor has modeled their device, then they can run the first order transfer function that you found in parallel with the hardware. So that's what this model does. Now, if I run this guy, you'll notice that this transfer function does not match the hardware, right? So let me run that first. So if I run that and I maximize this, the yellow is your measurement and the purple is from the simulation. But this transfer function does not match my device, right? Like, for example, first of all, the DC gain that I measured from the graph is about 26.2, right? So I'll use 26.2, and then the time constant is probably about like 0.13 or something like that. That I didn't measure, so I'm just gonna. And it's okay. So I load this up, and then I can just start this. So there, now you're getting a better match. So again, I'll maximize my screen, and there we have it. So the DC gain is right on because I've measured that. I did not measure the time constant because I don't want this to become a course on an online course or anything. But I could just tune it, right? So this is a bit too fast, and then I could just go back and say, all right, let's add a bit more delay, rerun it, and it's very, very quick, right? So that matches a bit better. So that's a better match, right? Then you can tune it as you wish. That's this very quick model validation lab. And again, you can plot your data offline if you want. All right, let's get into a controls example. So if we go and let's say we want to do a PD controller. So in here I have so many of you are interested in controls. So here it is. Here's a very standard PD control. So the PD control is right here. So again, I'm using the same 3 blocks, but right now I'm going to measure the encoder because I'm doing position measurements. So the encoder is being transferred into radians. I have the loop back, the negative feedback, and the proportional gain and the negative gain, all using standard Simulink blocks, nothing fancy here. So let's go ahead and run this. Of course, you could use your model and then derive what PD gains are necessary to reach like a certain peak time and overshoot. You can do all that, and that's part of the lab of the Courseware we offer. Okay, well, I'll go ahead and start this. So there we go. So here is the position. All right, so you'll notice I'm getting a bit of an overshoot. Another thing that you can do is you can tune stuff on the fly. So if I go ahead and start increasing the derivative or velocity gain, then you'll notice that I'm getting less overshoot, right? So it's become more damped. So I'll switch this back to 0.05. If I bump up the proportional gain to 0.5, then my peak time gets reduced, much faster response. But again, I get a bit more overshoot, right? So then I would have to increase my derivative gain to remove some of that. So what I'm showing here is that there's certain things like gains and parameter. You can do it on the fly as the controller is running, right? You can do this all on the fly. So those are all using the inertial disk add-on module. So let's switch gears now, and I'll show you something that's a little bit more advanced, the pendulum, right? So we also have a number of labs for the rotary inverted pendulum. We have 6 labs offered, right? The one I'm going to show you is a swing up and balancing controller. So this one is the last. It's the final lab, right? So of course a student wouldn't be expected to just dive in this and without going through the required prerequisite labs, right? So they have to know about balancing and modeling and stuff like that in order to get to this point. But this kind of shows you that you can develop fairly advanced algorithms on this on the QUBE Servo device, right? So the swing up, again, very very popular experiment in controls. There's different ways to do it. In this way, we're using what's called an energy-based controller, right? It's actually based on a paper written by Carl Ostrom and Dr. Furuta in, I believe, in '96, right? So it's presented at CDC, and it's been used a lot. We've used it with many of our devices. It's nice because it basically uses the nonlinear dynamics of the pendulum, of the 1 degree of freedom pendulum. So using the nonlinear dynamics of the pendulum, which are in this block here, the swing of control. Right, so it's using the nonlinear dynamics of the pendulum, and it's also using the pendulum energy. So by an energy control, not to get too much detail, but it's a lot like a position controller where you give a position set point. In this case, I'm giving an energy set point because the energy set point in this case is the potential energy is like 38 or sorry, it's like 30 millijoules, right? So that is my set point for my energy controller. So it's going to try to reach that target, and then I switch to a balance controller that they would have designed previously. That's basically what it is. All right, so I think that's about it. I need to run so in here, this runs the pendulum. It loads up the state space matrix. It loads up the balance gain and stuff like that. So it loads up all my values for my model. So what you can do here is you can click on this to generate your code as well. And then once your code is built, you're ready to launch. One question we often get as well is, can I change the controller? Of course you can, right? If you don't want to use the swing controller, then you could just delete this block or modify it and put in your own. That's no problem, right? So a lot of people, the common questions are, can I do a adaptive controller, robust controller? Can I do fuzzy logic? Fuzzy logic is very popular for swing up. Of course, you just delete this block, put in your fuzzy logic, and that's it, right? Okay, so, but for now, I will not design a fuzzy logic controller. I'm just gonna launch into this one. So there you have it, right? So it's a hybrid controller. You could think of it that way. So it swings it up when it's in the downward position. Once it gets within plus or minus 20-degree range, it switches into that linear state feedback controller, which you can see in the bottom of my schematic diagram. I'll just run it one more time. So you make sure the pendulum is still, and then you go QUARC, start, and there we have it. Right, you can disturb the pendulum and swing back up, right? So there you go. There you have it. That's basically I just kind of showed you from the hardware interface right up to what you can do with a swing up. So you can cover simple sensor actuator type stuff. You can do modeling. You can do PD, PI control, either position or speed with this QUBE Servo2. And then you can do more advanced stuff with the inverted pendulum and introduce state space and stuff like that, right? So in terms of the courseware, before I give you the Arduino, I quickly want to show you the courseware. So if you go to Quanser community courseware resources, we have most of it all online except the instructor versions, of course. But in here, all the lab experiments are within this. So for example, we have the fundamental labs, which is basically a listing of all the laboratories that are included, right? So we went through, for example, the integration and we went through bump test modeling. Or you can say, okay, for example, the swing up, okay, predefined lab sequence. So if I want to do, so this will suggest what you need to do in order to do something, right? So if you want to do the swing control, which I just demoed, what are the necessary labs, right? So I would need to know about the servo integration. I would need to know filtering, PD control, balance control, and then the swing control. Those would be the 5 labs, the minimum 5 labs that we need to go through before being able to accomplish the swing and control laboratory. We also have application labs. If you want to do steering control and cruise control, these are more like application specific. So it's using a visualization of a car, and you can do and you can control basically the car that's on your screen using the QUARC visualization, which QUARC also supplies. Very quickly, one last thing. If you there's tons of material here, so I can't we could spend another webinar just going through the various material that we have for the QUBE Servo system. But one I just want to show is textbook mapping. So in textbook mapping, this I'm going to maximize this and just zoom up on it. This is available on our website at multiple locations, but you can see, okay, up here is the 8 most common textbooks found around the world that are used in control system courses, right? So, for example, if you have the Dorf Bishop model control systems book, you can look up and say, okay, the bump test lab that I went through, or the or the PD control lab that I went through, where is that covered, and which section is it covered in this particular textbook, right? So it would name the section in. So this is called a textbook mapping guide, right? So on the left, it's all the labs that are supplied with the QUBE Servo, and on the top, it's all the textbooks, right? So it maps those together. All right, I think that is about it for that. So now let's switch gears. I'm going to close MATLAB Simulink now, and we'll use embedded and I'll give you 2 quick demos with the Arduino, and then we'll launch into some questions, the Q&A session. Right, close this. So I will now switch this. I'm going to move this over here. I'll give you 2 demos for the Arduino. So let's first do the DC motor. DC motor here. So I'm already connected, as you can see. So all I'm going to do is connect this guy here, and then I'm going to connect the Arduino. So this is the Arduino Uno that I'm using. So you do have to set it up properly, right? Depending on which microprocessor board. So right now what we're doing, we have 3 examples right now, right? So we're going to be supplying example code for the Arduino. So there's basically 3 demos. The hardware interface that we kind of went through. There's the PD controller for controlling position, which I just showed with the MATLAB Simulink, and the balance controller, right? Not the swing up, just the balance, the inverted pendulum balance, right? So those are like the 3 like cornerstone or like key demos that will be included with the Arduino. So the first thing you gotta do, you gotta make sure that the most recent driver is installed for your port, right? So I got that set up here on COM4, and make sure you selected the right board, stuff like that, right? So make sure it's configured properly, and we'll have notes on that, of course. We'll make it easy on you guys. Okay, so the 3 demos are here. I'm going to open up the QUBE Servo control. Just going to go ahead and close that. So here is the example code, right? So it's very well documented. And to compile, you just go here. So I'll click on verify. All right, and then you upload the code. So I'm just going to start running it right now. So there we go. So you see it's turning. So this one, they got a bit more, it's a little bit more fancy, right? So it goes between red and green, showing that the code is running in the Arduino, and of course it's moving, right? Now what you can do is also open up the serial monitor, and this shows you, I'm just going to stop the auto scroll. This shows you the status and the pendulum angle, which will have connected, and the current and stuff like that. So going through a bit of the code here, just to show you, so I'm not going to go through initialization, but I want to show you at least where the controller is, just to give you a bit of an idea, right? So it shows you how to talk to the encoders, right? How to transfer counts to position, which is done right here, right? So you're converting the ARM encoder counts to radians. Same thing for the pendulum, measuring current. And then in here, here is the proportional derivative gains, right? So your KP, your derivative gain KD, you set those, and here's the control laws. So it's very, all this code is very readable, and then this will be transferred into PWM signals, or later on. So again, all the code thoroughly documented and modifiable Arduino code is offered with the system. Okay, so I'm just gonna click on reset there, and what I'm gonna do is actually, I'm just going to disconnect it temporarily. I'll remove this, and then I'll show you the DC motor. The pendulum. So this will be the balance controller. So I'm going to close this down here. Of course, it starts running the previous controller, but that's the case. I'm just going to open up the pendulum, and then I will upload that. So the pendulum, of course, has a lot of the same code as before, right? So if I go through here, it's the same initialization and code accounts and all that stuff. And then when you get down to the right here, here's your control law, right? So the state feedback is basically a double PD controller, and it's all done through here. So there's your controller. I'm just going to reset it to make sure, rerun the code, because I want to make sure the pendulum is motionless before I start. All right, and then I'll go ahead and open up the serial monitor just to make sure it's running. Okay. And yeah. And there we go. So when it's engaged, it goes from yellow to green, showing that it's engaged. And there you have it. So this, again, does not have the swing up. It has the balance. Those are the two main examples, including hardware integration, that we're giving with the Arduino. So if you press on reset, it'll stop that. And that's about it. All right, so that's the end of the demo. So I guess we can open up to